Yes, thank you, Margie, and I thank the organizers for organizing this wonderful conference. I already have learned a lot, and I'm planning to continue learning. I'm also planning not to go over time. This is about a result in a paper that ended up being almost 50 pages long, and I have two anonymous referees of combinatorial theory to thank for it. So I will try to avoid technical details, and I hope that the only reason that my speaking and the slides will be out of sync is not some technical issue, but because it's on purpose. The slides give you formulas, visual informations, complicated definitions, and I will try to just highlight the main ideas. Okay, and so in this spirit, I think I will skip this outline slide because it's very rudimentary and start with the definition of a hyperplane arrangement, which hopefully everybody knows. We look at hyperplanes in a real vector space, and what we care about is what kind of regions are created by this and how many of them. And here is my favorite example, the linear arrangement. Okay, the official definition of the linear arrangement is something like this. You take all hyperplanes of the form xi minus xj equals 1, where I is less than j. Now, this is not what you see in the picture. You see the intersection of this arrangement with the hyperplane where we set the sum of the variables to be 0. There is a good reason for that, namely, when you only look at equations of the form xi minus xj equals a constant, you can increase both variables by the same number and you are still in the same region, hence all regions would be unbounded. By intersecting this with this hyperplane, you get one bounded and 6 unbounded regions. I will also mention another paper where instead of this, they talk about relatively bounded regions. Okay, and my main reference when I started this research was the paper of Postnikov and Stanley on the deformations of the braid arrangement. And so this slide is fairly technical. What I would like to stress is that the ideas I am trying to present is apply to all hyperplane arrangements where the hyperplanes are in have equations of the form xi minus xj equals some number. And in these cases, of course, you can associate a graph to such arrangements where you can think of the xi, xj as vertices and then these constants as labels. The rest in this slide is language of Postnikov and Stanley, the truncated affine arrangements where xi minus xj goes from the negative of a minus 1 to positive b minus 1. Special instances are linear arrangements, shear arrangements, and so on. These will come up later, and if they don't, it doesn't matter. Okay, so I am still learning how to count regions in a hyperplane arrangement. I arrived learning about this topic decades later than people who are really doing this. But I would like, from my perspective, it seems that one key approach is to use Zaslavsky's formulas, and this, my research is not about this. I am just mentioning in order to avoid confusion and in order to praise Zaslavsky for creating a framework where you don't need to know anything specific about the hyperplane arrangement at the beginning, but you can come up with formulas, and then depending on your specific arrangement, you can try to introduce combinatorics. So what's this idea? You take the intersection poset of the hyperplanes, you use the Möbius function to define a characteristic polynomial, and then you substitute -1 into this characteristic polynomial to get the number of all regions and +1 to get the number of all bounded regions. I call this inclusion-exclusion based because somehow to my mind it seems that we should think of the regions as closed cells, and then we take care of the overcounting. And then in specific instances, you can use the finite field method if the coefficients are integers. And when your arrangements are sort of graphical, then you can use Whitney's formula. And then there is also the gain graph method. Okay, now instead of that, what I would care more, and this is what my research was about, is that you can also think of regions being defined by sets of inequalities. Okay, so if you go back to our previous example, here I see three hyperplanes, each has two sides, and 2 to the 3, I should be seeing 8 regions. But I don't see 8 regions, but one is missing. Why? Because if I know x1 minus x2 is greater than 1 and x2 minus x3 is greater 1, this forces x1 minus x3 greater than 1. I cannot have here x1 minus x3 less than 1. Okay, and so here are a few examples where inequalities were used to label regions in a hyperplane arrangement. There is the extended Xi arrangement, which has a Paxtonly labeling, and an Athanasia, this Linusson labeling. And just when my paper got accepted, I got a warning that the labeling I looked at based on the Athanasius, this Linusson labeling for the Catalan arrangement was already found by Bernardi, and those are the annotated M sketches. Okay. Now, I also mentioned that you don't have to go with intersecting your hyperplanes xi minus xj equals constant with the sum of the coordinates being 0. And this is done in the work of Hopkins and Perkinson, where they use the same variant of Farkas lemma I also use. Okay, so for my approach, there are two key lemmas. One of them is Carver's variant of the Farkas lemma, and the other is the flow decomposition theorem of Gallai, and I am proud to mention that Gallai was my father's thesis advisor. Okay, so first of all, before we get lost here, why is the Farkas lemma a natural choice here? We said that the way we can exclude certain possibilities is that certain inequalities imply others. Now, the Farkas lemma in simplest human terms says the following, that if you have a set of linear inequalities and a next linear inequality contradicts the previous ones or is a consequence of those, you can always prove that by taking some non-negative linear combination of your premises. So the proofs are very easy, and the Farkas lemma tells you how to find them. Okay, now for some reason, I bumped onto the same variant of the Farkas lemma that was also used by Hopkins and Perkinson, which is strange in the sense that the Farkas lemma in this original form is about strict linear inequalities, and there is a rephrasing with non-strict linear inequalities. It basically says that, well, I can make the same statement about non-strict inequalities, but then I want to make sure that and I think this should be strictly greater than 0, that my proof is not the proof of let's multiply each line by 0. Okay, the proof is not trivial. It's originally drew to Carver from the 1920s. You have some reference to limits superior and stuff like that. Okay, now the other idea is that if you have a circulation, you can on a graph, you can always decompose it as a positive linear combination of directed cycles. Okay, and so here is the next technical slide, and we can read it. You can read it. Let me explain it in human words what this slide is about. If all my inequalities are of the form xi minus xj is greater than some number or less than some number, then each region that's created is defined by a set of such inequalities. I call this a weighted digraphical polytope. And then what you can do is you can associate a weighted digraph to this. There is an edge from I to j of weight lowercase mij if xi minus xj is greater than mij, and there is an edge backwards of weight negative mij. You can also think of multiplying here both sides by -1 if there is an inequality this. We allow these weights to be negative infinity. If mij is negative infinity, then we keep that weight. If uppercase mij is infinite, it will also create a weight of negative infinity. Okay, and then the key theorem is the following, that if I look at the digraphical representation of such a list of inequalities, I get a non-empty region defined if and only if there is no cycle in the graph where adding up the weight of the edges around the cycle gives you a non-negative weight. The sketch is the following: direct translation of Carver's variant of the Farkas lemma gives you that there is an empty region if and only if we have a, so I would say, M ascending circulation. And then by the fluid decomposition theorem, we can show that at least one of the cycles contributing to a non-negative combination of such a circulation is M ascending. Okay, now before we go on, let me also mention that sometimes I get questions about is there a way to define a type B analog of this and such. What is easy to use Carver's variant of the Farkas lemma. You always get some combinatorial-like result using that. But then if you want to decompose it, then you need something like the fluid decomposition theorem. Currently, I am working on trying to describe type B cycles. Okay. Now, I would like also to mention this, that this is sort of a strange consequence that for the directed graphs, we are looking at here with their weights, what we can think of is that the weight is money I get for traveling. And then the condition is that I should not be able to make money just by going around. So Dijkstra's algorithm doesn't necessarily apply, but the Floyd algorithm does apply to these graphs. Okay, now going back to our example, in our example, the weight of each edge is 1 or -1, and actually it is easy to decide which one, because if a smaller I defeats a larger j, so this is an ascent, then the weight is +1, and if 3 defeats 2, that's a descent, the weight is -1, we don't need to write it down. And so we get back exactly the so-called semi-acyclic tournaments, which are already there in the Postnikov-Stanley paper, and I also mentioned that Shmulik-Ravid also came up with the same labeling, but now you see a natural, quote-unquote, natural explanation of why these label the region. Also, you should note that the only ascending cycle in this situation is 1 goes to 2, goes to 3, and goes back to 1. That's where I have more ascent than descent, and that's the missing digraph from this picture. The other thing you should notice here is that the only bounded region has the only digraph that's strongly connected, and actually this is a theorem which is true in general, that the bounded region are exactly the ones where the weighted digraph is M-acyclic and strongly connected. I would like to mention also that in the Hopkins-Perkinson paper, if you read it, there the arrows go backwards and they have unoriented edges, and those are the ones where in my setting directed edges would go both ways, and with this precision I can also have multi-graphs, they only have simple graphs. Okay, and so as a consequence for the linear arrangement, bounded regions correspond to strongly connected semi-acyclic uh, tournaments. Okay, I don't want to run out of time, so exponential arrangements, I am not going to define them. I would like to just mention that Stanley's formula about them can be also shown in this way, that when you count the regions, it's like you count all the graphs. And so you can also partition your graph into strongly connected components. And then on each one, you create a strongly connected graph, because a bad cycle can only live within the same strong component. Okay. Okay. Uh, Okay, so then one in my setting, deformation is separated if zero is part of this set, and uh, then we have a straight linear order. The other extreme is when we have just two elements in I mean one edge in each direction, a simple graph. Okay, and then let me go back, sparse deformation. Okay, so one thing I can prove using my theory is that an interval order in my setting represents a bounded region if and only if its comparability graph is connected. Uh, Stanley mentioned these interval orders yesterday. Okay, now here about the Pakistani labeling, I would like to mention then just that you can do the Pakistani labeling for extended shear arrangements. And in my setting, this would be um, you look at the weight of each edge. um in a linear extension, and the sum of the weights will be the separations, and you add the inversions, and then you can just copy Stanley's proof from the shear arrangement to the extended shear arrangement. Now, this is another very important fact, the simplification lemma. Look at this picture here. The weight of 0 plus the weight of -1 here already implies the weight on this edge. And the converse is also true, namely whenever an edge can be omitted because it's whenever an inequality can be omitted because it's a consequence of the others, then you can also prove it graphically. And one situation where this works really nicely, this is the ceiling diagrams of Armstrong and Rhodes. I came up with a definition of she-ish arrangements, which contains all she and extended she arrangements. And there you can exactly describe which ones are the ceilings in the ish arrangement and in generalizations thereof. Uh, by looking at the labels. Okay, about Athanasia, these Linusson diagrams, those are also labeling the extended shear arrangements. What I came up with is a slight generalization where the largest bound and the lowest bound can slightly differ. So this is a common generalization of the Catalan arrangement and the extended shear arrangement. Okay, in these, we have parking functions counting the regions, and Athanasiadis and Linusson didn't work this out, but there is an exercise in Bruce Sagan's book that can be used to introduce parking trees and count the regions. And so therefore, we can define beta extended shear arrangements and generalize the formula for the number of regions of the shear arrangements. And the proof uses a colored variant of the prefer code algorithm. Okay, and then finally about Catalan arrangement, what comes out from this setting is exactly Bernard's annotated M sketches. And then there is another one, which is sort of mysterious, uh, where you define the weight just by the levels of uh, an A Catalan path, and it works. But the proof is just like Stanley's proof, that you prove it's an injection and then you know it's a bijection because the numbers agree. And I would like to conclude with a conjecture. Okay, I didn't have time to go through the gain notion of the gain function. That comes from this paying money approach, that you can define the gain function as the largest amount you can gain by going from an initial point to any other point. And in several settings, including the Catalan arrangements, you can choose this gain function in a way that you get money in each edge, and you have trees just like in the Dijkstra algorithm, computing this and using these. Uh, it seems to me that uh, the number of regions is a polynomial of A, and so the A Catalan number, the nth A Catalan number should be written as a Catalan number of polynomials of A. Okay, so that's a weird thing. I have tried small examples where I could work this out and prove this, and I don't know how to prove this in general. Am I really over?